Chinese researchers have unveiled a breakthrough that could redefine the future of electric vehicles. Scientists from Tsinghua University, Shenzhen, and Tianjin University have developed a silver-based flexible armor coating that allows solid-state batteries to operate for more than 4,500 hours and even maintain stable performance at -30 degrees Celsius. This innovation directly addresses the mechanical cracking that has hindered progress in solid-state batteries. Solid-state batteries have long been seen as the holy grail of electric vehicles. They promise higher energy density, faster charging, and greater safety since they replace flammable liquid electrolytes with solid ones. Yet despite all the progress, they've been held back by one major flaw. Their internal structure tends to crack under stress, limiting both lifespan and performance consistency. At the heart of the issue lies something called the solid electrolyte interface, or SEI. This thin layer forms at the interface between the lithium metal anode and the solid electrolyte. In theory, it's meant to protect the battery's internal materials and ensure smooth ion flow. But in practice, it's brittle, like a thin sheet of glass covering a balloon. When pressure builds up from fast charging, high current, or temperature swings, that glass-like layer shatters and loses its protective role. Once the SEI cracks, lithium starts to pile up unevenly, forming needle-like deposits called dendrites. These dendrites don't just reduce efficiency. They can short-circuit the cell and destroy it over time, leading to rapid capacity loss and thermal instability. Engineers tried making the SEI harder to resist damage, but the harder they made it, the more easily it fractured under mechanical stress and thermal expansion. So, despite solid-state batteries having impressive test results in small setups, they failed when scaled up for real-world conditions like winter cold, fast charging, or thousands of daily use cycles. It wasn't about chemistry anymore. It was about mechanics and material behavior under stress. That's what makes the new Chinese breakthrough so exciting. Instead of making the SEI harder, the researchers asked, what if we made it flexible? By rethinking how the protective layer behaves under pressure and temperature changes, they've tackled the single biggest obstacle keeping solid-state batteries out of our cars and onto production lines. This is where science meets creativity, and it changes everything we thought we knew about how batteries should be built. The research team led by Professors Feiyu Kang and Yanbing He at Tsinghua University's Shenzhen campus, alongside Professor Quanhong Yang at Tianjin University, decided to rethink how solid-state batteries handle pressure and temperature variations during continuous operation. Their goal wasn't to make the SEI layer tougher. It was to make it adaptable, resilient, and capable of maintaining stability through countless charging cycles. They developed a new silver-based coating made from compounds called silver sulfide, Ag₂S, and silver fluoride, AgF. These materials form what they describe as a flexible armor for the SEI, strong yet able to bend slightly when the battery expands, contracts, or undergoes stress during charging and discharging. The inspiration came from nature. In the lab, this design worked wonders. When tested under intense conditions, the batteries equipped with this coating ran continuously for over 4,500 hours without major degradation, a remarkable milestone compared to standard solid-state cells. Even more impressively, they stayed stable for more than 7,000 hours at -30 degrees Celsius, a temperature that would normally cripple most batteries and severely limit ion transport efficiency. The secret lies in how the silver compounds behave. The combination of Ag₂S and AgF allows the SEI to flex without cracking, maintaining a smooth and uniform surface where lithium ions can move freely at consistent speeds. This prevents uneven buildup, stops dendrite formation, and dramatically extends the cell's lifespan under both high current and low temperature environments. What's groundbreaking here isn't just the numbers, it's the approach. Instead of chasing higher energy capacity or faster charging speeds first, the researchers went after reliability. They solved the Achilles heel of solid-state batteries' mechanical failure under real-world stress. In simple terms, they built a battery that doesn't fall apart under pressure. This means electric vehicles could finally perform reliably in cold climates, charge faster without degrading, and last longer than ever before. Now, the big question becomes, how soon can this innovation leave the lab and hit the road? The implications of this discovery are enormous. If scaled successfully, this coating could make solid-state EV batteries not just safer, but practical for mass use. Electric cars could maintain full performance in freezing winters, handle ultra-fast charging without damage, and keep their batteries healthy for years. This would remove two of the biggest barriers that have slowed EV adoption: durability and temperature sensitivity, while also increasing consumer trust in next-generation battery technology. For consumers, it could mean vehicles with longer range, longer warranties, and fewer battery replacements. For automakers, it could open the door to slimmer, lighter battery packs that don't require heavy cooling systems, reducing both cost and weight. It also hints at lower production waste and improved sustainability, since batteries would last longer before needing recycling or replacement. This breakthrough also goes beyond electric vehicles. It could play a huge role in renewable energy storage, where reliability in harsh environments is essential. Wind and solar farms in cold regions could use these batteries to store energy more efficiently year-round, supporting more stable power grids and improving clean energy resilience during extreme weather. However, the researchers themselves emphasize that this isn't ready for factory lines yet. Producing this silver-based coating at an industrial scale is still a challenge. It involves precise layering, careful temperature control, and cost considerations since silver isn't a cheap element. Engineers will need to find ways to replicate this flexible armor with affordable materials or optimize the process to keep prices reasonable while maintaining the same stability and performance benchmarks demonstrated in the lab. That said, the innovation provides something the global solid-state battery race has desperately needed: a credible path forward for long-term stability. While companies are also racing to commercialize their own versions, China's approach could push the entire industry closer to real-world applications. The takeaway? It's not just about squeezing more power into a battery. It's about making that power reliable under any condition. This new design philosophy could redefine how we think about battery engineering for years to come, finally turning decades of promise into something that works beyond the lab. China's flexible silver-based armor coating could be the breakthrough that turns solid-state batteries from laboratory dreams into road-ready reality. It's not just about more power. It's about a smarter, stronger, and longer-lasting design that can handle the stress of real driving and harsh climates. While mass production challenges remain, this innovation could reshape how electric vehicles are built, stored, and powered. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries, and don't forget to leave a comment below. Thank you for watching, and see you next time.